Hello everyone. Today I'll be talking about the stable marriage problem. It is a classical problem in mathematics and computer science that seeks to find a stable matching between two set of participants, such as men and women, doctors and hospitals, or students and schools. So let's first start by defining the problem. So given that there are n men and n women, all of the men and women have ranked all the other members of the sex in an order between 1 to n to express their preference. So now that we have all the matching preference between all the men and women, we now have the task of arranging a marriage between all the men and women together in such a way that no two unsatisfied people of the opposite sex who would both rather have each other than their current partner. So what does it mean for there to be an unstable marriage? Uh, if there exists two married couples such as M1W1 and M2W2, such that M1 desires W2 more than W1 and W2 desires M1 more than M2. So in this case, the opposite partners should have been more stable than the current ones, because in the current situation, someone prefers someone more, and the other person also prefers that person. So such a pair is called dissatisfied. Now let's see an example for stable marriage. So say we have three men, M1, M2, and M3, and three women, W1, W2, and W3. And they have the following preferences as shown in the slide here. M1 rank W2 more than W1 more than W3. This means that M1 would rather be paired up with W2 more than W1 and W3. So we have all the preferences for the 6 participants here. So for the given preference set here, there are 3 possible stable matchings for this arrangement. So first matching is M1W2, M2W3, and M3W1. If we notice in this matching, all the men get their first choice, but the women their third preference. And there are 2 more stable matchings here. And in the second matching, everyone gets their second choice. And in the other one, women get their first choice, but men their third. Note that in this example, the stable marriage doesn't mean that everyone gets their best preference. So stable marriage doesn't need to be optimal for all. All it needs to do is find a stable matching such that the pairs are satisfied is the best preference that they could get. Now, a naive approach would be to start with a random marriage of all the participants. And until all the marriages are stable, we choose a dissatisfied pair and marry them off and their partners off with the other potential partner. Note that this approach is not optimal, and this may end up in like never-ending loops of people changing partners again and again. But this may find like stable matching at some point in the recursion. Now we have another algorithm proposed by Gale and Shapley. So we will now discuss like a variation of that algorithm, which is the men proposal algorithm. In this, the men propose to the woman, and the women decide if they have to accept the proposal or not. So there are 4 main steps for this algorithm. Initially, all the men and women are unpaired. And in the second step, we see that if all the men have a partner, then we have found a stable matching and the pairing is done. And ignoring that pair, we move on such that they don't match up again and find the other partners for if there are any other unpaired men. So for the unmatched men, let's say, let's call him P. And in the next step, we see that if P has already proposed to all the girls, then we have to terminate the algorithm because none of the women in our given set have accepted his proposal. Otherwise, let H be the woman that P likes the best among those he hasn't approached so far. So now P goes on to propose to H. So if the woman H has already been proposed to by a man, she prefers to P. She rejects P's proposal because she has a better preference there. Otherwise, she accepts P. And then they become paired in the current matching. And whoever she was previously partnered with now assumes the role of P. If she had no previous partner, then she takes up the proposal of P and they become matched, and the algorithm continues at step A1. Otherwise, it continues at A2. Note that at each step of the algorithm, there will be a partial marriage, and the unmarried man proposed a marriage to his desired partner who has not yet rejected him. So then the woman decides whether to accept or reject the proposal based on her current matching or preference set. So in this algorithm, there could be a total of n square proposals. So the runtime complexity of this algorithm is order of n square. Now we discuss the correctness of the algorithm. So in the current setting, all the people involved have their preference listed with all the available partners. That means that all the men have their own, given their preference for all their partners, and the women have also done the same. So everyone has their other sex as some in some preference order. So there is this preference set. And now once a woman gets married, say it's in the final stage or like a partial engagement in between, she will stay married throughout the step after she gets partially married, because she cannot go unmatched with that person. If she finds a better preference, she will change the partner, but she never becomes unmarried after she gets paired with a person. If a man is unmarried, since there are equal number of men and women, then there is a possible partner who is also unmarried. Given that if she is unmarried, she will accept that proposal. Thus, in the end, we say that everyone will get married in this algorithm, hence it is correct. Now, we discuss the stability of the algorithm, if it gives the stable matching or not. So imagine our algorithm gave out a stable matching at the end of its runtime. But assume that there is an unstable pair. So if there was a pair of M and W who are married but are unstable. Let's say M1 prefers W1 over W. In the algorithm, every man has proposed to all the women. So at some point, he must have proposed to W1. So there are two cases here. If W1 accepted the proposal in the past, but at the end, we see that W1 is matched with someone else. So that means that in the end, W1 preferred someone over M. So M1 and W1 wouldn't be stable in the final matching. And in the other case, if W1 rejected the proposal, she is already married to someone she prefers over M. So we can say that in the end, all the marriages given by this algorithm are stable. So now let's see an implementation of this algorithm. Here I have a Python code with the rankings that were denoted in the beginning of our presentation with M1, M2, M3, and W1, W2, W3. And we start the matching and we go one after other until all the matches have been done. So we just run this algorithm once. So we start with each man here, since it is we chose the variation where men propose to the women. So each time when M starts, he goes with his preference and is engaged to W2 here, and M3 gets engaged to W1 and M2 with W3. So this pair which is found here is also one of the stable matching that we discussed earlier. Now, as I said before, this version of the algorithm that I've discussed before is the version where men propose and the women make the decision. So this version of the algorithm is men optimal. That means that men are married to their best possible partner, whereas it is women pessimal. So the women are married to their worst possible partner. Since they are the one who makes the decision and not propose to the partner, they have to accept the men who have proposed them before. So men end up getting the best possible partner in this algorithm. So the other variation of this algorithm could be where women propose and men make the decision. So this variation would be women optimal and men pessimal. So now let's discuss stable husbands. So as we have seen before, there could be multiple stable matchings for a given set of population. So stable husbands are list of all the men with whom a woman could be married to in a stable marriage. So given all the list of stable marriages, we see the list of men who the woman is possibly within a stable marriage. So all the list of such husbands, we call them stable husbands. So in a paper called Stable Husband by Donald Nutt and et al., uh, it is proven that given that n boys and n girls rank each other at random, the paper shows that a particular girl has at least this much and at most this many different husbands in a set of the Gale-Shapley matching that we have discussed before. And with the probabilities approaching one as the population grows to infinity. So for this version, the paper uses a randomized algorithm. So now let's discuss the randomized algorithm. So in this variation, instead of fixing the preference sequence in advance, we simply let them unfold to whatever extent the algorithm needs them as it runs. So whenever a boy is asked to propose, he proposes to a random girl as if there is no preference set for him, and that is chosen randomly from among the girls he hasn't tried yet. And whenever a girl receives her kth proposals, she may accept it with the probability of 1 by k. So we here in this case, we simplify the algorithm by assuming that each boy has amnesia and cannot remember the girl he has previously asked for. So instead of keeping track of all the rejects that he has gotten before, we just keep it running as many times as possible. And when there is a redundant proposal made, such proposal is always rejected. So this algorithm may run forever because the redundant proposals are being made again and again. But we will see that certain aspects of this algorithm's probable behavior are kind of fairly easy to analyze. And that is also in part because it never terminates. So for this, we use a principle of deferred decisions here. And at solving problems, it is not necessary that all the random choices that had to be made at time step t had to be made in advance. Rather, it is sufficient to say that at each step of the algorithm, we fix only that random choice and that needs to be revealed at that step. So this makes all the complexity of assuming all the random choices beforehand go away, and the analysis becomes easier here. So for our problem, we assume that the men's lists are chosen independently and random, and women's lists can be arbitrary, but they are fixed in advance. They have their preference set. So now we go into the analysis of this random variation. So there are let me remind of the two algorithms here. One is the main proposal algorithm that we have, and now we have the amnesiac algorithm where man makes proposal randomly. So let TP be the random variable that denotes the number of proposals made during the execution of our original algorithm, and TA be the number of proposal made in this amnesiac version. So we can see that probability of TA greater than M, that ends up being always more than or equal to the probability of original algorithm, because in this algorithm there's always multiple redundant random proposals being done. So the advantage, so we do this because there is an advantage in analyzing TA over TP, because in this version we only need to count the total number of proposals made. We don't have to care about all the previous proposals and the kind of rejects that they are getting, which makes it more complex. And this also gives us like an upper bound on our TP. So the upper bound on TA is also an upper bound on TP. So to do analysis on this, we make a connection with the coupons collector problem. So this was discussed in class. So some of the results used here are directly derived from the class. So here we define x to be a random variable the value of which is the number of trials required to collect at least one of each type of coupon. So we know that expectation of x is nhn, where hn is the harmonic number, and this is of order of n log n. Now let's define an event EIR. Let this be the event that the coupon of type I is not selected in the first R trials. So since all of these events are independent, we can just multiply the probability of this, which is 1 minus 1 over n, and multiplication over R trials will give us this probability here. And this is less than e power minus R by n. And if we choose R to be beta n log n, that is R to be the expected value here, the probability of this expected of this event is less than or equal to n power minus beta. Now we would like to estimate the deviation from the expected number of trials. So probability of x greater than r is like the probability of all such events, the union of all such events. So in the R trials such that none of them are chosen, which is less than or equal to sum of all the individual events here. And for our chosen R beta n log n, we see that the probability is less than or equal to n power of minus beta minus 1. So we found the bound on the probability for our trials to be greater than the expected value. So to get the deviation, to get kind of a deviation from the expected number of trials, we make more analysis here by choosing another number that I will discuss. So when x deviates from the expectation, which is previously we chose beta n log n, by some linear factor of n, which is cn. Let's see any real number. And we would like to discuss the deviation when x is beta n log n plus cn here. So for some m, we use the principle of inclusion and exclusion here. Probability of all the union is equal to this term here. So alternatively, we add and subtract all the intersection of the events here. So this pkn is the probability of all the intersection of the events, all the k events here. So we know from the Boole's inequality that union of probability of union of all the terms is less than or equal to individual summation of all the probabilities. So this might give us the upper bound on the union, but Boole's inequality can also be generalized to find a lower bound as well. So these bounds are called Bonferroni inequalities or Boole's Bonferroni inequalities. So these results are directly from the principle that we have of inclusion and exclusion, because in that principle, all the odd terms are added and the even terms are subtracted. So we see that the union is always less than or equal to all the summation of the odd terms and greater than or equal to summation of all the even terms here. So this gives us the lower and upper bound on this probability. So let's say S and K is a summation of all the probabilities that we have discussed before from the principle of inclusion and exclusion. So we can say that probability of union of all these events is bound by the at the lower side by the even terms, and on the upper bound by the odd terms here. So we now have a bound on the probability of all such events. So let's try to see the behavior of the term P and K that we have defined before. So we see that the K intersection of all these events here are equally likely. So summation of all these terms is nothing but summation of all the n choose K terms. So we can simplify it by saying that P and K is n choose K into probability of intersection of these events. So we see that the probability of intersection of all the events is the probability of not collecting any of the K coupons in the first M trials. So this probability is nothing but 1 minus K over M. And for M trials, since they are independent events, it's to the power of M. Now, as int approaches infinity, as the population goes to infinity or the number of coupons go to infinity, we see that this limit tends to this term here. And when we substitute m with n log n plus cn, we see that this term nicely simplifies to this small term here, e power minus ck by k factorial. In the last slide, we've seen that p and k is n choose k into 1 minus k by n power m. And by substituting the above expression in this term, we see that as n tends to infinity, the probability of this term ends up being e power minus ck by k factorial. So we have defined this term sk from the principle of inclusion and exclusion here. So substituting the value of pk here in terms of j, we get this term. So this term is nothing but the expansion of 1 minus e power minus e power minus c. So this one can be simply written as limit k tends to infinity. This term is nothing but this here. So for the sake of simplicity, let's say that f of c is the term here. So as limit k tends to infinity, sk is equal to f of c. So since sk approaches to f of c as k tends to infinity, we can say that for all epsilon greater than 0, there exists some k greater than 0, so as that for any k greater than the term, the difference between this is very small or negligible, and we express this as this term here. The absolute difference between sk and fc is less than epsilon. So we know from the inequality before that probability of union of all such events is bounded by these terms. So using the upper bound from this term, we can substitute in our previous inequality here, sk minus fc, saying that probability of union of all these terms minus f of c is less than or equal to some other epsilon term multiplied by a constant here. So from this, we can say that as n tends to infinity, probability of union of all these terms is nothing but f of c, which is 1 minus e power minus e power minus c. From this, we can say that as probability of x greater than the value of m that we choose, n log n plus c, the value approaches to 1 minus e power minus e power minus c, which is very small. So to summarize what we have done till now, we found that the worst case complexity of our algorithm is order of n square. And in the average case, the expected value of n hn. So the complexity turns out to be order of n log n. And the deviation from the expected case is very small. So for n log n plus some constant term into n, the deviation that we have found here is very small and negligible. So there are many real world applications for this algorithm. So dental residents and medical specialties in USA, Canada, and some parts of UK use this to match the students with the residency programs. So before earlier, like it was used for the benefit of residency program. It was not intentional, but the residency were making the proposals and the students had to accept it. So that was residency program optimal. But now it has been changed to the other way around. Now it is student optimal, where students start making the proposals, and the residency program, they choose to whether to accept the student or not. And this algorithm is also used for assignments of student to high schools in New York. So in any case, where we have set of participants and set of participants who want to be matched up with each other, this algorithm can be used. Thank you.